Hello and welcome to this lecture on visual image interpretation. My name is Lina Eklund and I'm a lecturer at the Department of Physical Geography and Ecosystem Science at Lund University. I usually teach GIS and remote sensing, Earth observation, and like I said, today we will talk about how we can look at satellite images and study them visually. So the overview of this lecture, we will talk about what visual image interpretation is, what it can be useful for. We will talk a little bit about scale and resolution, different combinations of bands, image quality, image interpretation process, what should we interpret, and the reflection characteristics of different objects. So this is meant to give a brief introduction to the field of visual image interpretation. But if you want to go more in depth, you might need to look at other literature to learn more specific things. So visual image interpretation is the process of extracting quantitative and qualitative information of objects at the Earth's surface. We do that by using aerial photos taken from airplanes, for example, satellite images. We can also use drones nowadays. It's quite common. And this type of interpretation is a very intuitive analytic process where you are using your eyes to see and identify objects. Because of that, it's important to gain experience, to become really good at interpreting the features that you see in an image. You need to have thematic knowledge of them. You need to understand what you are seeing and what you're looking for. And oftentimes it's very important to have field experience so that you've seen these objects on the ground and know that they are there. Right, so back in the day, image interpretation was done with actual physical images using stereoscopes to see in 3 dimensions. And nowadays we mainly use, for example, orthophoto interpretation or satellite image interpretation on the screen, on the computer screen. And this is what I will talk mostly about in this lecture. So there are many usages, and I would say in general it's really important to just take a look, see if there are satellite images or aerial photos for the area that you're interested in studying, and then you learn a lot by just looking at the images. But it can also be used not just for recognizing what's happening on the ground, but more systematic mapping of land use and land cover, for example, or to collect training and validation data for land use and land cover mapping that would be more automatic. It's also very useful when you're digitizing features for GIS, for example, digitizing roads or houses or lakes. We can also use it to monitor environmental damages, for example, oil spills or flood impacts. Remote sensing or visual image interpretation is also used in archaeology to identify areas that are of interest to archaeologists. And we see on the right here some 2 examples of images from the Sentinel-1 satellite, which shows what kind of features we can see from satellite images. A very important aspect of the images that we're working with, both for visual interpretation but also for more automatic mapping, actually, is the pixel size. So these 4 images are of the same area. They have different resolutions. And you can clearly see that the left-hand image of 100 meters resolution doesn't really show much at all. We can't really see features. It's very blurry. It's hard to separate anything. But if we move down to 25 meter pixel size, we see a bit more of a pattern. We see some darker areas, probably tree covered, and some brighter areas, probably more open lands. And so basically you can see much more when you increase the resolution, you get more detail. If we move to 10 meter resolution, which is the common resolution for the Sentinel satellites, for example, or for the visual bands at least, we see much more. We can actually see the edges of agricultural fields, we can see the edges of forests, and maybe even see that the forests are different, that some forests are darker than the others, indicating that they are coniferous, and the brighter ones are deciduous forests. And this is something that I know because this is an area in Sweden that we have visited before, so we have former knowledge about the area. It might be much more difficult, probably much more difficult if this was an area that I had never visited, that it's not an area I have knowledge of. And then finally, if we go down to 1 meter resolution, which we can do when we have, for example, aerial photos, which this is, we can almost see individual trees. And definitely if we zoom in, we can see individual trees. And we can see all the edges, we can see the roads very well, we can see houses, we get a lot of detail. We can even see within the agricultural field that there are differences in reflection in different parts of the field, for example. So we get more information by increasing the pixel size, and this is also very important if you're doing a land cover classification, because it determines or it affects the minimum mapping size, so the minimum size of an object that you can map. So with the 25 meter data, maybe you can map a field here, you might be able to map all of this forest, but if you go down to 1 meter, you can actually map houses and roads and individual trees. So there's a big difference in what you can map, depending on what resolution your data has. Right. It's also important to be aware of the different colors and band combinations. With visual image interpretation, we usually work with 4 bands at least. We work with the blue, green, red, and near infrared. And if you have heard a lecture about electromagnetic energy, you know that these different colors have different wavelengths, different places in the spectrum, and the blue, green, and red are the visual wavelengths, whereas the near infrared is the wavelengths that we cannot see, that are above 0.8 micrometers, and this is where we get a lot of information about vegetation, because vegetation reflects a lot of infrared. So this is an important thing to know when working with visual image interpretation. And depending on what you are interested in mapping or identifying, you can choose to work with different types of bands. Then you can also combine these bands, and combining them gives the image different appearances, and it can enhance different objects. So here I've just put together the same area but with different band combinations. And this one lower right here is the natural color using the blue, red, or blue, green, and red wavelengths, whereas the one opposite here is the false color composite, where you have switched out red for infrared band, and you can actually see which areas has a higher infrared reflectance, which is not really possible to see in the natural color image. And then you can combine the different wavebands in different ways. So it's the same thing, but with different combinations of bands, right? So if you are planning an image interpretation project, for example, if you're planning to classify land cover using visual image interpretation and not an automatic approach, there are some steps that you should take depending on the exact project, but generally we think it's very important to study the existing information. Look at the images, look at supporting information, what do we know about the area that we're about to map, and then select the image material depending on the purpose and scale. So if you want to map a large area, maybe you cannot have 1 meter resolution aerial photos. Maybe you need to go with satellite images of 10 meters or even coarser. Depending on how much time you have also, it's a time issue. Bigger areas and more detail takes more time, of course. Yeah. And also you need to decide on what kind of detail you need. Do you need to see individual trees? Is it okay to not distinguish between tree types or crop types? What is it that you need to know for your mapping project? Or after your mapping project is done, actually. So you have to think a lot about these things. And then when you have decided, you start by creating an interpretation key. What should be included in the legend of the map that will be the result of your mapping, for example? What should be included? How does it look like? What are the definitions? How can you ensure that if you're more than one person doing the mapping, how can you ensure that everyone is on the same page? Everyone understands what is the definition of an agricultural area or a forest, for example. Here you also need to decide on the smallest mapping unit, the area of the smallest mapping, the width of something. I mean, it can be you can have a very narrow but long line. Is that relevant to include? How long should it be to be included? These kind of things are important to decide on before you start the project. And then if possible, you go out and collect training data. You go out to the field, you go visit some points that you may have predefined. What can you see? What do you want to see here? What does it look like from the ground? And also, that can be hard to do when you have data from different years, and if you may be doing a project going back in time, you can only collect training data for the present time that you're in the field. So this is important to consider, but there are ways to estimate whether has this been an agricultural area for a long time? Does it, I mean, has it changed since, since the image was taken, for example? Then it's time to start mapping, digitizing the areas that you're interested in, identifying the objects, classifying, and trying to be as consistent as possible. Follow the interpretation key and the definitions you have there. Right, and then you can, when you have mapped these objects, created a map or a GIS layer, you can quantify, you can check how much vegetation cover there is, how many rock outcrops or tree crown cover. Then you can analyze these data, and if you have classifications for more than 1 year or more than one point in time, you can also do a change assessment, which is really interesting and relevant to see how has the land cover changed, for example. Another important aspect is to collect evaluation data. You will need to, you should evaluate your map and make sure that it's accurate enough. And The most common way to do that is, of course, to go out in the field again, collect evaluation data, and make sure that you collect data in a very unbiased way. So you do a random sampling. What are the areas to go to? Make sure you have a sufficient amount of areas you visit. Collect these data and then use them to calculate map accuracy by comparing the data from the field, the ground truth data, with the map results you have from your mapping. And then you produce your final results and report. So this is an example of how you can go through planning an image interpretation project. Yes. So when we do interpret images, there are so many things we can look at to figure out what it is that we're seeing. Commonly, we look at the color of the Earth's surface. If we're using a natural color, we can see, is it green? Does it have vegetation? Or does it look gray? Is it blue? Is it red? What's going on there? And the tone of it, how green is it? Is it very dark green or bright green or these kind of things? But we can also look at shape and texture, for example. We can look at the geometry of something. We can look at the placement and the context. And then we can bring in additional information which may help us to identify what we are seeing. So if we talk about color and tone, we realize quite quickly after looking at satellite images or aerial photos that many objects are very similar. Even though they are different, they look similar in color. It is also important to note that many objects are, they vary over seasons. So, for example, a forest in Sweden might look different in March compared to in April, May, or in the fall when the leaves may turn red or yellow. So it changes a lot throughout the season, which is important to consider when you're looking at the color. And then also important to think about is that the color the tone of things looks different in different parts of the world. It's not always comparable, so that's why it's important to understand the context of the study and look at many examples. We can look at shape and texture, which can give us clues about whether there are humans present, if the humans are affecting the land surface. And yeah, we can also see that like the context makes a big difference if we have many shapes together. Can help us interpret things like, for example, the fact that a river usually ends in a lake. So rivers are connected to lakes, and we know that it should be. And this is something that we as humans know, but computers that are automatically classifying things may not know that, or at least very basic algorithms do not have that understanding, which is why we are better than computers generally at interpreting satellite images. Yeah. When it comes to human influences also, usually if we see very right angles, very sharp angles, squared patterns, that's a clue that we have humans present. But on this image here that we're showing, the opposite is actually the case. Well, there might be some human structures in this image, but this river that takes a very sharp turn is actually not due to human influence, but because of the geology of the area. So there are also exceptions, and you can see that the geology influences. There's a lot of lines here that are quite straight. So probably the geology has influenced how this river is directed here. Yeah, and then we can look at shadows, and I will come back to shadows eventually, but they can actually help the interpretation of features. The context is super important. So where in the landscape are we finding this object? And does it make sense? For example, if we find a wetland, if we identify a wetland on a hilltop, does that make sense? Usually you don't find wetlands on the top of hills. Do we find farmlands in the city? Well, it depends on what context we're studying. So it's a matter of how these objects are relating to each other. We can also see if we know that there's bedrock in the surface that can give us an indicator of what kind of environment we have. There are also exceptions, obviously. In some cities there are riding ranges with pastures, grazing areas for horses, which may look like an agricultural area, but yeah, it's a gray zone maybe. The climate can also help us. If we know what the climate is like in a place, it can help us interpret our images. For example, we usually don't find trees in the desert, so we have to be a bit of a detective to look at all the clues in the landscape and see what makes sense here. And this is also where it's important to have knowledge about the field. It really helps to know the area you're studying. Different objects also have different reflection characteristics, and this is a topic that you can go into more in detail, but I will take the overall most important points. So there are two types of reflectors in theory. You have specular ones that are flat, mirror-like surfaces. They reflect very sharply the incoming radiation. And then you have diffuse reflectors, which are rough surfaces where the reflection goes in many different directions. And it's important to know that the actual Earth surfaces that we are looking at, they are not either or, but they are often a combination of the two, or somewhere in between specular and diffuse reflector. Yeah. And we have something called albedo, which is the average percentage of incident radiation that gets reflected by the land surface. And so the higher percentage, the more is reflected. So for example, we know that fresh snow has a very high albedo. It reflects a lot of incoming radiation, and that is also why snow is so bright. It's white. And then when snow gets older, the albedo lowers to 50 to 60%. Asphalt, on the other hand, is very dark. It doesn't reflect a lot of light. That's why it's black or dark. About 5 to 10% of the light gets reflected. Water is interesting because it depends on a lot of things. For example, the position of the sun when the image is taken, or when the light is reflected. So water can have between 8 and 80% of reflectance, which is a very broad thing, a very broad range. But water generally appears quite dark on satellite images, suggesting that, so when the sun is up, when we are taking the satellite images, daytime satellite images, water generally has a very low reflectance, a low amount of radiation reflected. It absorbs a lot of the radiation. Light soils have 25 to 45% reflection. Deciduous forest, 15 to 20%. So it's a bit brighter than coniferous forest. Coniferous forest usually appears darker, has a reflectance between 10 to 15%. But it's important to remember that these numbers are, of course, generalizations. So it depends a lot on what part of the spectrum we're looking at, what time of the day, what exact type of land cover we are looking at. So it varies a lot. So you can see these as a general, like giving a general idea of how much of the radiation is reflected. Yeah, so if we go into the trees or different objects, how do they reflect light and how can we see them? So trees, of course, look different depending on what species we're looking at. Which also determines the texture or color of the leaves. The health of the tree is important. It also affects how the light gets reflected, and also the morphology of the tree crown, because how does it look? How is it shaped? And then also the spaces between tree crowns, because if you have space between and you can get soil reflectance, maybe in the same pixel, if you don't have a high resolution, then that also affects the amount of reflection that you measure. Yeah, the spectral composition and intensity of light is also important. The conditions of the atmosphere, which is something that I'm not dealing with in this lecture, but it might come up in a different lecture, hopefully. But just the fact that things happen to the radiation in the atmosphere, and that affects what trees or what any kind of land cover looks like. There are also indirect factors like the soil type and moisture, how that reflects, the slope, if the trees are on a slope, and the aspect of that slope. The date and time of observation, naturally. So if you are looking at trees before the leaves have come up, or after they have fallen off, if they are deciduous, and then whether or not you are looking against or away from the sun. So where is the instrument taking the image, and how what is the position of the instrument in relation to the sun. So many factors influence what we can see. Shadows, they are important because they may actually hide things, they may obscure vision, make it harder to interpret an image, and they tend to alter the color characteristics because they are re-emitted radiation from the atmosphere, and so it's reflecting other type of radiation than the direct sunlight. So this may be tricky, but shadows can also be positive. They can reveal the shape of a tree crown, for example, if you're lucky. So they can be both good and bad. The time of the day, or the time of the year, has an influence. So time of day affects the shadows, of course. If you are into archaeology, low angles are maybe more useful to give more shadows, so you can actually see the structures that you're looking at from the side. The time of the year is also important. It determines how much light you have. You have different phenological developments, for example, the leaf status that I've mentioned before. Time of year also determines if there is vegetation or no vegetation. Maybe the crops are planted but haven't come up yet, or they have come up, then it looks completely different. You might have snow and ice. This is maybe more specific to my context in Sweden. We have a lot of influence from snow and ice sometimes in certain parts of our country, but that's not necessarily the case for many other countries in the world. So how can we identify land covers? And I just have some examples that might be relevant to you who are listening. If we look at open lands, for example, cultivated with a lot of crops, it can be hard to separate different types of crops. So there it's important to have contact with the field. You go into the field and collect training data. It can be good to have information about the climate zone, to know what kind of crops can you expect in an area. Also for croplands, you don't only look for the color for green fields, but the patterns are relevant. So usually the fields are quite square shaped. If they are smooth and have like a very similar color and texture, they tend to be cultivated. But if there are a mix of different patterns or colors or tones in the field, it may be grazed. If you have trees or stones in it, it's more likely that it's grazed. Yeah, and then after harvest, it's better. It's a good idea to use post-harvest images for soil mapping, because then you see the naked soil, which you cannot see when there's vegetation on the ground, or which it's hard to see when you have vegetation. So these are some things to consider when mapping. Soils and geology is an area where it's quite useful to use aerial photos or satellite images, but usually then it's better to use a multispectral recording where you have a very like a high number of bands, so you have very specific parts of the spectrum that you can look at. Well, some things to think about here is that humidity reduces reflectance. It makes it look darker. And dry soils have a higher reflectance in longer wave bands. So towards more infrared reflectances, the drier soils have a higher reflectance. The texture, and also in the red wavelengths. Usually dry soils look more red. The texture, surface roughness can also affect the reflectance. So if you have fine textured sands, you have high reflectance. And an example of that is if you look at a desert area, they usually look quite bright because you have usually quite fine sediments or particles. Yeah, you can get some ideas about the drainage patterns, if there's a karst landscape, if there are fissures and weaknesses in the bedrock. You can see maybe faults and tectonic indicators from satellite images or aerial photos. It can be difficult to separate the types of rocks. But for example, sandstones are often softer shapes, and limestone and shale are often sharper shapes. So you can sort of use this information to infer what it could or could not be. The vegetation growing on the surface is also an important indicator for the geology of the soils. And usually it's a good idea to use images from early spring or late autumn when you don't have as many leaves up and you might have harvested, so there isn't so much vegetation cover. This of course depends on what part of the world you're in, but it's important to consider when doing soil mapping that you need to actually have exposed soil, or it makes it so much easier. And then, yeah, you can also identify geomorphological aspects, looking at shapes. Then we have water, and water is interesting because it can look very different. But like I said before, it has a very low reflectance, and especially a low reflectance in the visual wavelength, so between 0.4 and 0.8 micrometers. In higher or longer wavelengths than 0.8, there is no reflection because it's all absorbed. There are some exceptions to this, because you might have very low, not so deep water where you can see the sea floor or the lake's floor, or you might have vegetation in the water that comes through. So sometimes you can see a reflection in water in the infrared, but generally the reflection is very low or zero. So you can use water to quantify the influence of the atmosphere, especially when you know these things, that it has a very low reflection in infrared. And it's useful to, for example, look at water to detect pollutions with algae blooms, sediment loads, and oil spills. So there is a lot of visual interpretation focused on water as well, even though it has quite a low reflectance in all wavelengths. So to summarize, we can detect a lot of information from satellites and aerial images. But to do that, if you want to do a project, you need to consider what time of year you are interested in, or what time of year you're looking at. That gives you an idea of what you can expect. You have to consider the resolution. What can you actually see in the image that you're working with? Or what do you need to be able to see in order to decide what image you want to use? You need to figure out what wavelengths you are seeing or you want to be using, because that determines what you can actually see. Maybe you want to combine different bands together to see something specific, to highlight, for example, vegetation using near infrared in a false color composite. And you have to consider different reflection characteristics. And there's a lot of information here about different land surfaces. So here I suggest reading a bit more about these things, trying to figure out what you need for your project. Training, you have to train yourself. You have to, this skill to interpret images is, it is a skill that you have to train. You have to exercise it and learn and get better at things. You also need to validate your interpretation. And that often requires field access. So to know if you're right or if you're good at what you're doing, if you're good at interpreting, you also have to validate your classification or your interpretation. And then planning is very important. If you're planning to carry out a land cover project, you need to plan it well and have all the steps decided so that you know what to do in what part and in what order. So that's all I had for now. Thank you very much for listening. Have a nice day.